Today we are going to learn about the EM algorithm, applying to real-world clustering. We'll explore its fundamentals, step-by-step implementation, and practical application in data science. By the end of this video, you'll be equipped to apply the EM algorithm to clustering tasks effectively. Welcome to this introductory video on clustering, a fundamental technique in data science. Clustering is the process of grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. It's crucial for deriving insights from unstructured data, which is common in today's data-driven world. Clustering is used across various domains, such as marketing for customer segmentation, healthcare for identifying disease patterns, and more. It forms the foundation for more advanced data analysis tasks like classification or anomaly detection. The Expectation-Maximization (EM) algorithm is a powerful statistical tool used to find maximum likelihood estimates of parameters in statistical models, particularly when the data is incomplete or has missing values. The EM algorithm consists of two main steps: the expectation (E) step and the maximization (M) step. During the E step, the algorithm estimates the missing data given the observed data and current parameter estimates. In the M step, it computes parameters that maximize the likelihood function, assuming the missing data is known. This iterative process continues until convergence is achieved. The EM algorithm is widely used in clustering, especially with Gaussian Mixture Models, GMMs, where it efficiently estimates the parameters of the Gaussian distributions that best fit the data. Applying the EM algorithm to clustering involves several steps. First, initialize the parameters of the model, which can be done randomly or using heuristics like k-means clustering to set initial cluster centers. Next, perform the E step by calculating the expected values of the latent variables using the current parameters. This involves computing the probability that each data point belongs to each cluster. Then, perform the M step by updating the parameters to maximize the likelihood of the observed data given these expected values. This step typically involves recalculating the means, variances, and mixing coefficients for each cluster. After completing the M step, check for convergence by evaluating the change in the log likelihood function. If the change is below a predefined threshold, the algorithm has converged. Otherwise, iterate the E and M steps until convergence criteria are met. The choice of initial parameters in the EM algorithm is crucial, as it can significantly influence the convergence and outcome of the clustering process. Random initialization is a simple method but can lead to the algorithm getting stuck in local optima. To improve results, you can leverage domain knowledge to set more informed initial parameters. For instance, if you're clustering customer data, initial parameters based on demographic segments could be beneficial. Alternatively, using k-means clustering to determine initial cluster centers can provide a good starting point for the EM algorithm. It's also advisable to evaluate different initializations and choose the one that consistently leads to the best clustering outcome, ensuring robustness and reliability in your results. Convergence issues are common in the EM algorithm, where the process can be slow or get trapped in local optima. To handle these problems, consider adjusting the convergence criteria, such as setting a smaller threshold for changes in log likelihood or limiting the number of iterations. Regularization techniques can also be applied to prevent overfitting and improve convergence behavior. It's important to monitor the log likelihood function to ensure it steadily improves and stabilizes as the algorithm progresses. If convergence issues persist, it may be worthwhile to explore alternative clustering algorithms such as k-means or hierarchical clustering, depending on the data and application context. Implementing the EM algorithm in Python is straightforward, thanks to libraries like scikit-learn that provide efficient tools for clustering. The Gaussian mixture class in scikit-learn simplifies the implementation of Gaussian mixture models using the EM algorithm. In this practical example, we'll walk through a step-by-step coding tutorial on how to apply EM to a dataset. We'll start by importing necessary libraries, then initialize the Gaussian mixture model and fit it to our data. We'll also visualize the clustering results to gain insights into the data structure and clusters formed by the algorithm. Additionally, we'll analyze the convergence behavior and performance of our EM model, evaluating its effectiveness in clustering our dataset. Evaluating the performance of models clustered using the EM algorithm involves several key metrics. The Achaik Information Criterion, AIC, and the Bayesian Information Criterion, BIC, are commonly used to assess the quality of the model in terms of parameter fitting and complexity. For assessing cluster quality, the silhouette score provides a measure of how similar a data point is to its own cluster compared to other clusters. If ground truth labels are available, comparing the clustering results with these labels can offer additional insights. Interpreting the clustering results helps derive meaningful insights and identify patterns in the data. It's important to iterate on model parameters and configurations to enhance performance and ensure the clustering model is robust and effective. The EM algorithm is just one of many clustering techniques available, each with its strengths and weaknesses. Comparing EM with other methods, such as k-means, reveals differences in handling data variance. While k-means assumes equal variance across clusters, EM, particularly with Gaussian mixture models, can model different variances, resulting in more flexible cluster shapes. Hierarchical clustering, on the other hand, offers insights into data hierarchy and relationships, which can be valuable in certain contexts. Density-based methods like DBSCAN are suitable for datasets with varying density and noise. When selecting a clustering technique, consider the characteristics of your data, the insights you wish to derive, and factors like computational efficiency and scalability, especially for large datasets. In conclusion, the EM algorithm is a powerful tool for clustering, offering flexibility and precision in identifying data patterns. To master its application, it's essential to carefully initialize parameters, evaluate model performance, and iterate for optimal results. Understanding the strengths and limitations of the EM algorithm enables you to apply it effectively across various domains, from marketing to healthcare. By leveraging the insights gained from clustering, you can drive data-driven decisions and enhance your analytical capabilities. Remember, the journey to mastering EM involves experimentation, analysis, and a keen understanding of your data.